Hi, myself Dr. Pradeep Das, Research Associate Professor from Department of Chemistry, SRM Institute of Science and Technology. Today we are going to discuss the last part of our organic photochemistry presentation, and in the last part we are going to discuss some very interesting photochemical reaction. First one is the intermolecular photoreduction. Second one, photodimerization of alpha beta unsaturated ketone, and the third one is the rearrangement of enone and dienones. Now we are going to discuss about the intermolecular hydrogen transfer and this intermolecular photoreduction process. So usually photoreduction of carbonyl compound is one of the best known of photoreaction. So in its initial step, the mechanism involves the transfer of a hydrogen atom to the oxygen atom of the carbonyl excited state. For a donor molecule, which may be a solvent or an added reagent or ground state molecule of the reactor, ketone undergoes photoreduction in the presence of a variety of hydrogen atom donor. So these hydrogen atom donors are secondary alcohol, toluene or cumene, and the reaction is usually a bimolecular reaction. If you let us consider this example, we can see this is the aryl ketone. In presence of light, it is going to convert it into excited singlet state. Followed by intersystem crossing, it is coming to the excited triplet state. Then this is the diradical where this electron can both on the carbon and on oxygen. Then this one react with the A alcohol molecule. And here we can see that what will going to happen, that this hydrogen from this carbon atom of this alcohol is going to transfer to this oxygen atom, and it is converted this carbonyl radical, and this one is the another radical. Now this radical, this generated from this alcohol, is react with another molecule of ketone and produces this molecule, and the second hydrogen is got transferred from the OH group to produce this carbonyl radical, and it is again converted to this ketone. And these two diradical is go for a type of reductive coupling type of reaction to produce the pinacol. In the second example, we have seen the similar thing where the H nu can convert this carbonyl radical which react with the methanol to produce this carbonyl radical, and this radical generated from the alcohol after the hydrogen transfer, and finally leads to give this product. Now this is the another example where we can see that this molecule, this is a ketone molecule, and this ketone molecule is react with this secondary alcohol in presence of light to produce this type of pinacol, and acetone is a byproduct. So here this reductive coupling type of reaction happen after this carbonyl radical, two carbonyl radical undergo combination. Now we are going to discuss about the photodimerization of alpha beta unsaturated ketone. Let's see the first example where we can see a cyclohexenone in presence of light undergoes 2+2 cycloaddition reaction to produce this two product, and both they are two different isomer of 2+2 cycloaddition product. The pi2s plus pi2s photodimerization reaction proceeds by the involvement of the 2 pi electron from each ion, and the two pi bonds converted into intermolecular sigma bond. Again, we can see the same example of the photodimerization of the cyclopentanone by this pi2s pi2s, the 2+2 cycloaddition reaction product. Now, the photodimerization of alpha beta unsaturated ketones provides a further class pi2 that is the 2+2 cycloaddition, and is demonstrated for a 3-methyl cyclopentane 2 enone with the formation of head-to-head dimers and head-to-tail dimers, as we see in this example. And this alpha beta unsaturated enones absorb light of wavelength is 300 nanometer and get the N2 pi asterisk excitation. So this reaction is believed to occur from the excited triplet state because intersystem crossing is very efficient for that reaction. While for the pi to pi state triplet excited enone also cause the dimerization as happened. Here we can see. Now, if we consider this is another example where two piridones are known to undergo photodimerization through pi 4s to pi 4s cycloaddition reaction. Now we are going to discuss about the rearrangement of enones and dienones. This is a very important class of reaction. So usually, let us start with the cyclopentenone derivative. So the cyclopentenone basically it is alpha beta conjugated carbonyl compound. So this alpha beta unsaturated carbonyl compound, the cyclopentenone, mainly gives a alpha cleavage reaction and 2+2 cycloaddition reaction. And this 5,5 disubstituted derivative undergo rearrangement reaction to the cyclopropyl ketone as shown in this example. And the rearrangement arises from the pi n to pi aesthetic singlet state and has to be carried out in the very dilute solution to prevent the dimerization. So this only the purpose of use the dilute solution to prevent the dimerization, to avoid the dimerization. The substrate at first undergoes Norris type 1 type of cleavage, leading to the formation of diradical. Recombination of this diradical leads to the formation of ketene as we observe in the Norris type 1 reaction. And this ketene reacts with the protic nucleophilic solvent to give the final product. Now, if we see here the example, here this cyclopentenone derivative in presence of light going for the N2 pi-aesthetic excitation to produce the singlet excited state. Then in the singlet excited state, this bond is going to break and this will produce the diradical. And then this one can undergoes this ketene derivative and these two radical again recombine to produce the cyclopropane. So this is actually ketene derivative of the cyclopropane. Then it is treated with the alcohol to produce the ester. If we treat it with the water, then it's produced the carboxylic acid. Now we are looking to the cyclohexanone rearrangement. So alpha beta unsaturated cyclohexanone give two type of rearrangement. Usually it gives two type of rearrangement. So these rearrangement are possible when the bimolecular reaction, that is the cycloaddition and the dimerization, are suppressed by the use of dilute solution. So here the same strategy is used. So the dimerization and the cycloaddition can be avoided by the use of dilute solution. And the two prominent rearrangement are the dipymethane type of rearrangement, that is we recommend as a path A here, that is the migration of the aryl group, and another one is the lumiketone rearrangement, that is the path B, that is the migration of the carbon atom of the cyclohexane ring. And the rearrangement are carried out mainly in the presence of tertiary butyl alcohol as a solvent. The dipymethane type of rearrangement arises by the 1,2 migration of an aryl group, and the lumiketone rearrangement arrives without the migration of a group. So in this case, the carbon atom of the cyclohexene ring migrates, and the migration of the aryl group of position 4 leads to the formation of a bicyclo 310 hexene 2-one, that is the lumiketone. Similarly, migration of a carbon atom of the ring, that is the migration of a C5 ring carbon atom, leads skeletal change, and this skeletal change also gives the 310 hexene 2-one derivative. So there are usually a path 1, that is the migration of a aryl group, and another one is the path B, that is the migration of the carbon atom of the cyclohexene ring. So both these things are happening. Either it will going to follow the path A, either it will going to follow the path B. So both type of rearrangement can be sensitized using propionophore and quench using the naphthalene. And this shows that both reaction proceed via triplet excited state. And the rearrangement with ring migration occurs from a pi to pi triplet excited state. Whereas the rearrangement with the aryl migration occurs from a N2 pi asterisks triplet excited state. So that is the basically difference. Ring migration happens from a pi to pi asterisks excited triplet state, and aryl migration happens from a N2 pi asterisks excited triplet state. And this is supported by the observation that a 4-alkyl 4-aryl cyclohexenone undergoes rearrangement with aryl migration in benzene, that is a non-polar solvent, but with ring migration in aqueous methanol, that means it is a polar protic solvent. Let us consider this example. Here this one is a 4-alkyl 4-phenyl cyclohexenone. In presence of light and benzene solvent, the non-polar solvent, N2 pi asterisks excited state, the reaction is going to happen, and it will leads to give in benzene. In benzene we have seen with the ring migration, but in aqueous methanol or polar protic solvent the ring migration is happening. On the other hand, if we carried out the reaction in benzene, that is a non-polar state, then we can see that this rearrangement of the aryl migration is happening. Now we are going to consider about the Lumi-ketone rearrangement. So what is the Lumi-ketone rearrangement? Lumi-ketone rearrangement is mainly gives by 4,4-dialkyl cyclohexenol, which involve the shift of C4-C5 bond to the C3 and the formation of a new C2-C4 sigma bond. So this mechanism is usually favored some workers involved in a radical path shown in the scheme 1. I will show in the scheme 1 in the later slide. And for the transformation of a 4,4-dimethyl 2-cyclohexanone into 6,6-dimethyl bicyclo-310 hexane 2-1 on photolysis in the solvent tertiary butanol. Now, if we see that next, so now discussing the last slide, that we told the mechanism favored by some person who are working during the course of the several reaction of organic photochemistry. So here we can see they postulated this mechanism for this cyclohexenone derivative in presence of light or tertiary butanol solvent. It can convert it into singlet excited state due to the N2 pi asterisks transition. Followed by inter-system crossing, it is going to convert it into the triplet state. And this triplet state, in this triplet state, there will be this bond migration happen and it produce the radical at this C3 carbon atom. Then the shift of the C4-C5 bond on the C3 carbon atom to produce this tertiary radical and a 5-membered ring. So the 6-membered ring is going to convert it into a 5-membered ring attached with a tertiary radical, followed by the bond formation between the C2 and C4, finally giving rise to this product. And here, as far as this molecular transformation is concerned, the change of the solvent also leads to give the variety of product. So when we change the solvent to acetic acid, then a pronounced effect on the product formation. Here we can see if the same reaction is carried out in presence of light in acetic acid solvent, we have seen the number one product that is produced in 20 to 25%, and the second product is produced as 30 to 40%, and the third product is produced as 5 to 10%, and all these products are produced. Now this difference is only observed when we change the solvent from tertiary butanol to acetic acid. So this Lumi ketone is not isolated from the reaction mixture because it is unstable to light, and in the presence of acetic acid, and is readily converted into 2-isopropyl cyclopentane 2-in-1-one, and it is proposed that as an N2 pi asterisks state favors radical intermediate in tertiary butanol or in non-polar solvent, and pi to pi asterisks state predominantly favored the deuter ionic intermediate that forming acetic acid and shown in this scheme 2. So here we can see this is the formation of this H nu in presence of acetic acid, singlet excited state followed by intersystem crossing. It is get this deuter ion and this is converted into this structure. Then number one, when this type of rearrangement is going to happen, by this it is come to this bond to produce this ketone, then it will come to this and this attachment is happening. That is completely ionic reaction and this is unstable, finally leads to get this product. That is the 5 to 10% products. Number 3, and then these deuter ion structure again react in acetic acids to produce this product. This is the number 2, 30 to 40%. And finally, it is also giving to this mechanism as shown in the scheme 2, the finally nucleophilic attack by this acetate anion, it is converted to this number 1 product 20 to 25%. Now, if we go for these another kind of mechanism, that is the dipymethane kind of rearrangement, we have seen that this is the aryl substituted cyclohexanone derivative. And this reaction is carried out with benzene in presence of light. So N2 piastridic tangence is going to happen. It converted the singlet excited state followed by the intersystem crossing to get the triplet excited state. And this is the picture of the triplet excited state. That is the carbonyl radical. We can see that is a diradical actually. It is going to convert into this structure where this radical is generated at the C3 position. Then it is come back again here and this will going to transfer here. So we are getting this is a final product like similar, that is a dipymethane type of rearrangement. Now we are going to discuss about the rearrangement of dienones. So here you can see that is the dienone example, diaryl substituted dienone system. So one of the most important dienones is the crossed conjugated dienones for photochemical rearrangement. The 4,4 disubstituted cross conjugated dienone gives type B rearrangement. In the type B rearrangement of this cross conjugated 4,4 disubstituted 2,5 cyclohexadienos, and the first photochemical steps occurs with a very high quantum. The value is 0.85. So here if we give the light, type B rearrangement is the first step to get this product number 1, which on treatment in the second step in presence of H2 and light converted into 3 different products. 2 are this benzene ring derivative, another is the acyclic compound. So the efficiency of the second step is actually substantially lower and the quantum yield is very low, 0.013, and the formation of this bicyclo 310 hex 3 in 2-one is formally analogous to a 1,2 acyl shift and occurs from the triplet excited state, N2 pi asterisk state. And in all reported cases, it is observed that the reaction proceeds from the N2 pi asterisk excited triplet state. And the unsaturated acid, this one, third product, the unsaturated acid arises from the singlet excited state. And singlet excited state, this will give the third product, that is the unsaturated acid, and the singlet excited state arises from the bicyclanone 1, and the phenol are produced from the triplet excited state of the bicycloenone system. So what Zimmermann found that this 4,4 diaryl cyclohexa 2,5 dienone system undergoes a rearrangement with velocity 4 times greater than the 4,4 dialkyl 2 cyclohexenone, and the reactive excited state is the N2 pi asterisk triplet state of the dienone system, and the reaction is thought to involve C3-C5 bond formation in the excited state followed by intersystem crossing and electron deactivation to give the deuter ionic intermediate. And this deuter ionic intermediate is then rearranged to the observed bicyclic product. So that is the main mechanism. So the C3-C5 bond formation in the excited state followed by the intersystem crossing, that is the ISC, and electron deactivation to give the deuterionic intermediate. And this deuterionic intermediate is then rearranged to the observed bicyclic product that we observed in the last slide. And also this is the bicyclic product. If we mention, this is actually the bicyclic product. This electron deactivation process is usually known as the demotion process, and this reaction takes place in the presence of sensitizer, and the reaction is quenched by the quencher, and in this reaction photophosphorescence phenomena is observed. So this result confirms that excited state is triplet and demotion process, that is pi asterisk to the n, pi asterisk n, that is the reverse process, takes place during the course of the reaction. According to the Zimmermann, the mechanism can be represented by this following way as shown in the skin 5, where we can see the H nu converted to singlet excited followed by ISC, then the oxyallyl biradical is converted to the triplet state. Again this triplet state go for the bond formation between the C3C5, again followed by the intersystem crossing, produce this singlet state, that is the D. Then it will come for the pi asterisk to n, the reverse process, that is the demotion, give the deuterionic intermediate, followed by the rearrangement, that is the bond breaking of the cyclopropanone ring, and migration to the carbocation to give this bicyclic product. Returning now to the example under discussion, we see that the product of the rearrangement can itself react further since it still has some enone system capable of undergoing excitation. And the following 6 deuterionic structures represented the various states of the electronic distribution. That is the 1, 2, 3, 4, 5 and 6. And these 6 structures are all the deuterionic structure and represent the various states of the electronic distribution. Now among these, 1, 2 were proposed to be precursor in the formation of the starting material. That's why they should now lead to the new products. 3 and 4 can undergo the phenyl migration, leading respectively to the 2, 3 and 3, 4 diphenyl phenol products. And both these products have been isolated from the reaction mixture. So here we can see that this deuterionic structure 3 can go for the 1,2 shift followed by the hydrogen migration to give this 2,3 diphenyl phenol. Similarly, the 4 go for the 1,2 shift. The similar phenomena, the hydrogen shift, can lead to give the 3,4 diphenyl phenol, and both are isolated in the reaction mixture. When the photolysis is carried out in aqueous dioxide, 2,3 diphenyl phenol is the major product and 3,4 diphenyl phenol is the minor product. In the presence of acetic acid, equal amounts of 2,3 and 3,4 diphenyl phenol are obtained. And only possible reason for this difference in the product formation or percentage of the product formation is the better electron delocalization with 3 than with 4 in the dioxide. But in the case of acetic acid, the protonation of the oxygen occurs and the delocalization is not a significant factor anymore. And the structure 5 can rearrange to ketene and forms an acid in aqueous medium, but 6 cannot.